Good afternoon, everyone. We ready? Okay, everyone, welcome to GNU Hurd, Unix Redesigned. My name is Neil Wallfield, and obviously I'll be giving this presentation. So I invite you to sit back and relax. I'll start off with a summary, introduction. I'll talk about the features of the Hurd, such as the new power that it can give you, and the added features of security. Then I'll talk about where we are, and as is traditional, I'll conclude. The Hurd has a relatively short history compared to Unix, although longer than most people think. It was started in 1990 by the GNU project. It was the last piece of a completely free operating system. It was before Linux. Linux was started in 1991 by Linus Torvalds, right? And had several goals. The most important was freedom. That's what the GNU project is all about. Freedom, GPL. We all know that. But it also had technical goals. The technical goals were to find an operating system that was much more powerful, more secure, and would go ahead and reflect on what had already been done. Unix was designed, it was extremely powerful, it was a good base. However, it was far from perfect. Even today it's not perfect. And I'll get into that in a little while. So the how. What are we going to do? Well, we're going to write a kernel in the same exact way we had written all of the previous tools. And when I say the previous tools, I mean the GNU utilities. Everyone uses them, and they're great. Powerful, flexible. The history of Unix. Unix was started in 1969 at AT&T. We all know that part. And if we look at the state of computers today, we'll see that Unix was created on very slow computers. Today, computers are generally over 1 million times faster if we just look at Moore's Law. 1 million times. That's enormous. I can't even imagine what 1 million times something is. But Unix hasn't continued to evolve with computers. The design hasn't really changed since the mid-'80s. And it's our opinion that Unix could change. It was built around certain assumptions. And we feel that these assumptions are no longer valid. They were chosen for small computers. The trade-offs that they made were they were good. Everything that the designers did was extremely well thought out. But that was for 1969 and the 70s. But today, 2001, 2002 next week. It's a whole nother millennium, whole nother ballgame. So, Unix, well designed at the time, but we need something new. And Unix just has not changed, even all of the derivatives. So what are these design flaws looking back now? Because they're not design flaws at the time. They're design flaws as we look at it today. If we were to re-implement Unix, what would we avoid? Well, regular users cannot really do anything. Sure, you can run your compiler, you can launch programs, but you have no control over the system. Can't run daemons, can't provide services. You log in, you do your work, and that's it. You want something more, you go talk to your system administrator. You say, hey, I need so-and-so, And if he feels like it, he'll give it to you. But he has to consider a variety of factors. And among those are security concerns. And that's another problem that we want to address. Security problems. Look at Unix. Compared to Windows, well, I mean, it's secure. There's no way you're going to break into a Unix system compared to Windows. But Unix has plenty of its own problems. I don't know how many of you follow BugTrack, but seeing that I'm at the CCC, I imagine a lot of us do. And buffer overflows are huge. Let's see, WUFTPD. Great bug. Great bug, right? And then there's plenty of SUID applications. Always problems with them. Not a remote exploit, but local. So Unix is not perfect. Linux. Linux is a rewrite of Unix, insofar as Linus went ahead and needed a free operating system, or wanted to work on a new operating system. And he used Unix as his base. Started in 1991, etc. With respect to freedom, Linux is pretty good. It's free software. It's under the GPL. But it has one major fault, fatal, in that the copyright is not assigned, and therefore it's undefendable. What this means is that there's no central entity which holds the copyright over Linux, such as the FSF or some other third-party foundation. For instance, X11, the X386 group, also does copyright assignments. This means that if a company goes ahead and takes the Linux code, uses it in their product, and then doesn't release it, it'll be quite difficult to go ahead and pursue them in court. So far, this hasn't been a problem. However, that's just so far. So, in the free software world, this is a very important issue. From a technical standpoint, Linux has nearly an identical API to Unix. There's clone, which is a slight difference. But all in all, Linux is basically the same idea as Unix. Not a lot has changed. And therefore, we see the same limitations. What I talked about before, buffer overflows, all those wonderful things. So how can we get around this? Well, let's first take a look at the different architectures. Unix and Linux are a monolithic architecture. In the kernel, you have all of the system services. If we go ahead and take a look here, we see VFS, TCP/IP, ext2fs, the virtual memory subsystem, the IDE controllers, all your drivers. Everything's in the kernel. What's outside of the kernel, in user space, is bash, ls, find, Emacs, etc. So what we're looking at here is a system where everything is in one address space, the kernel. We have a small C library, which basically provides additional functionality, and then just wraps system calls to make them user-friendly for application writers. And the kernel dictates the system policy. Doesn't provide mechanism, although it does. What's important to note is that the kernel dictates the policy. There's no way you can change this from user space. You have to go ahead and basically recompile your kernel. The other important architecture that we're going to look at is called a MultiServer Architecture. In this architecture, we go ahead and remove a lot of the components from the kernel. And we take them and we put them in user space. And we don't just put them in user space, but each one gets put in a separate process. So the ext2fs module, in Linux speaking, would go into user space as an ext2fs program. It's be launched by root, for instance. And would go ahead and provide the same functionality as the ext2fs module in Linux. And we try to remove as much as possible, especially all of the software drivers. But what's a software driver? A software driver is, in my terms, anything that doesn't really control the hardware. Something that is in the kernel for reasons of speed. It's not a real driver, it's fake. It's just there. For instance, TCP/IP and a variety of other things. And we just stuff them in the kernel because, one, that's where they've always been. And on Unix in 1969, well, yeah, put it in the kernel. Speed is pretty important. But in 2001, with computers that are over 1 million times faster, I don't know. System's much bigger, much more complicated. Where should it go? So in this model, we go ahead and shrink the functionality of the kernel, moving everything and putting it in user space. But the kernel, what's left of the kernel doesn't stay the same. We need to mold it a little bit more now. And in this case, we need to really develop the IPC and task management. Because now all the software drivers that were in the kernel are now in user space. This means that we have inter-process communication, which is going to be extremely important and has to be extremely fast. Extremely. Can't stress that word enough. I need a new word. Mega, super, galactic fast. So, lots of processes, all talking, all isolated, which is a huge difference between a monolithic architecture. Because in a monolithic architecture, everything is just together. Segmentation fault in a kernel module really means a kernel oops and a kernel panic. So, in this model, we avoid that. And a result of this is that the kernel provides mechanism, and it does not dictate policy. The servers do. The servers go ahead and provide the policy for us, because we can replace the servers. Each one is there, but they work together as a team, and we can make substitutions according to our needs. These servers, or translators, as we also call them, specifically in the Hurd world, are just normal programs. And they're accessible to other programs via the VFS. The VFS is the virtual file system. That's when you go ahead and you type ls and you see all your files. And even if there are 5 mounted file systems, it all looks like one big file system hierarchy. So the virtual file system goes ahead and is our address space to talk to other programs. Translators run as any user. And they're run by any user. This means that I don't need to be root in order to start a translator. I can run ext2fs as a regular user, no problems. Obviously, I'm limited. I only have my normal permissions. But if my ext2fs translator dies, it doesn't affect the system at all. I have no chance to compromise the system. And to talk to these different translators, it's just like opening a file. It's in the VFS. You go ahead, you run open. You get a file descriptor back. And we've gone ahead and designed our libc such that a file descriptor is all you need to talk to another process. So we're looking at a situation where the interfaces really remind us of Unix. It embraces that philosophy. And in fact, we think that we go ahead and take the Unix philosophy to where it was meant to be. Unix has always said, write small programs that do one thing, do it well, do it fast, and do it flexibly. So what we've done with the GNU utilities and what we're trying to do with the Hurd kernel. or the Hurd and the microkernel. This is very similar to the internet model. The internet model, our address space is our IPs. So you have an address, 192.168.1.1, for instance. And that's how you connect to a server. You open a socket, and then you can send messages. And TCP/IP, it's identical to our message passing system, insofar as TCP/IP does not understand what the contents of the message are. It understands a few small headers as a routing protocol, and it just delivers to a server. In the Hurd, we go ahead and have a client which sends a message. libc goes ahead and routes it appropriately, sends it via the kernel. Kernel takes the message, passes it to the appropriate program or server, and the server goes ahead and looks at the contents. So the kernel is just providing a route. It's the hardware, if you will, and that's all it is. All of the services are provided by the servers themselves. Using a translator, how can we actually go ahead and do this? Not just theoretically, but show me some code. It's actually quite simple. We've added an extension, obviously, to libc. It's the file name lookup function. This function goes ahead and takes a path, takes open flags, and a create mode. And what it returns is a port to a server or a file. This should look identical to the open function. And in fact it is. And in libc, our open actually is just a wrapper for file name lookup. And it adds a few semantics. So once we go ahead and actually have a port to the server, we can go ahead and use this port. And this is done using RPCs. RPCs are remote procedure calls. There are a variety of remote procedure calls. Hundreds, thousands. There are millions that have yet to be written. This is completely flexible. In Linux, you have several hundred system calls. And Unix, etc. In the Hurd, or in our microkernel that we're using, the number is significantly diminished. And the real system calls are now implemented via the servers, and we use a protocol. So it's just a matter of talking the right protocol, and there you go. So here I've gone ahead and used message to represent an arbitrary RPC. So what's actually going to happen here? Well, I'm going to assume that in path is a directory in the root file system. There's a directory in path called 2. And 2 is actually another file system. Okay? So we need to go ahead and deal with passing this message around. And how do we go ahead and actually do a full lookup? Because this isn't evident, not at all. The RPC to go ahead and look up a port in the VFS is dir lookup. Dir lookup takes a port as your starting base, and it takes a path relative to that base. In the Hurd, all processes have 2 ports, at least. They have the root file system port and their current working directory port. The root file system port is your root. It's not the root for the system, it's your personal root. This is quite important because it means that our ch root works a lot better than Unix's does. And then you have the current working directory, which we provide if we're using a relative path. But we're not. So, first we call dir lookup with the root port and the path to the server. Because we don't actually know that 2 is a mount point. The only one that knows that 2 is a mount point is the root file system. Because the root file system knows its hierarchy. It knows what its leaves are. Because the file system is a tree, the leaves are the nodes, the files, the symlinks, the FIFOs, the devices. etc. And in the Hurd, the leaves are also translators. So we need a protocol to pass to actually do this entire lookup. The protocol is handled between the servers and libc. The client initially issues a dir lookup for the entire path to the root file system, to its root file system. The root file system takes that path. It goes as far as it possibly can. It's able to resolve /path. And at that point, it realizes that there is another server listening on 2. And it doesn't know what that server's hierarchy looks like. It has its own personal sub-VFS, and that server just can't deal with it, because maybe it's another user. So we have a trust issue also. So in this case, we go ahead and we return a retry. We tell the client, here is the translator which we got to. And this is the amount of the path that we resolved. You now need to go ahead and finish the lookup with someone else. In this case, this is the child server, what I call that. Although there can be many different children. The client, this is all handled in libc, goes ahead and sees that it has to retry. And it sends another RPC. That server is able to successfully resolve the path, and it returns a send write to the server. Client goes ahead, sees that it was successful, had the appropriate permission, and it now holds a server port, can send to that server. And now finally we're able to send the message. So we take our message and we queue it on the appropriate port. The server looks at the message and sends back a reply. So in summary, the kernel is just passing the messages around. It's passing them around based on the ports. Okay, we had the root port. The root file system returned a port to a child, another file system. And finally we got a server port back. And we used that server port to send a message to the server. These are endpoints that the kernel understands and that we take advantage of. The virtual file system. This is one of the limitations of the Unix model. All the code that manages the file systems is in the kernel. What this means for us is that a user cannot take advantage of it. Can't take advantage of this because it's a big security concern. Corrupt the backing store means a kernel panic, possibly a system compromise. Either way, it's a pain in the butt for the system administrator. So users can do nothing. We just say there's a chance that something could go wrong. Better not to take the chance. Don't do anything. And because it's been so long, we've just learned to accept this. And if you really want to do something, you go ahead and you type sudo, and you switch to root, and you do it. But unfortunately, we're not all system administrator of our computers. So you talk to your system administrator. He yells at you. You go away. You're scared. Cry in a corner. Excuse me, I have bad memories. So we need a safe way to manipulate the VFS. Clearly, the Unix model doesn't cut it. Let's do something different. Let's take the protocol and just push it outside of the kernel. This way, there's no special privileges required because you can't compromise the kernel. You can't cause a kernel oops, etc. And hopefully, we also want the constraint that users cannot affect other users. For instance, if a server seg faults, this would be a kernel oops in Linux if a module goes ahead and gets a seg fault. Be like any other seg fault. For instance, you have a CS101 programmer. He thinks he just found a bug in the C library because his Hello World program crashed. But happily, that crash does not affect the system. It just affects him, and he thinks he's the hero of the world. So, only those that would rely on that program would actually be affected. It's a good thing. This is the normal model. If a daemon crashes, only those that use the daemon should be affected. And what we really want is that the system is completely unaffected, does not notice, sees nothing, just normal day-to-day maintenance. But there's an important question. Do we need a better VFS? Because, heck, we're all using Unix. It's great. Works well. Well, we can make NFS mounts, FTP mounts, GNU Tele mounts, all that beautiful stuff anywhere. Advantages of the Hurd. And we can work with files as though they're local. No need to run an FTP client. Just use CPLS. All of that beautiful stuff. No new interface to learn. It's great. Loopback devices can now be used by a regular user. I know I use loopback devices a lot, especially when you're creating disk images. And having to do it as root makes no sense to me. And then you can have fancy file systems like ShadowFS. ShadowFS goes ahead and takes several directories and creates a new idea of what the directory should look like. For instance, it might take two file system hierarchies and flatten them together. So, different ideas, really unlimited. But again, do we need it? We already have this already. We have auto mounters for NFS. We have bash extensions, so we can go ahead and do TCP/IP and UDP directly on the command line. And we have GNOME's VFS, so you go ahead and you type FTP:// and it works beautifully. Completely transparent. Or is it? Because every application must implement the same protocol for this to be a system-wide resource. And every application does not do this, and nor should they. And there's a question of security. So we have to have programs that trust each other, and we have to deal with trust issues. Or we could go ahead and just do what we're supposed to do. Put it where it belongs. The system's VFS. It's where the support should be. Write it once, use it anywhere. Right? I mean, this is it. So let's look at a translator in action. How does it work? Here I'm going to go ahead and set up a FTP-FS translator. This goes ahead and makes a connection to ftp.debian.org. And this literally goes right in the file system. Here I am in my home directory. We start off, we see that my identity is just Neil. I'm not the super user. No one special. Set up the translator. Use this nifnito command called settrans. Some nice flags, but details, we can avoid those details. But either way, the first argument that we see ftp.debian.org is the node where we would like the file system to live. So that would be the ftp.debian.org node in my home directory. The second argument after that is Hurd/ftpfs. This is the program, the translator, which is actually going to do whatever we're translating. And the do whatever we're translating is everything else. In this case, it's just simply ftp.debian.org because that's the host address. The final arguments are all interpreted by that translator. So it's all set up, and now let's actually see if it works. So I run ls on ftp.debian.org. Take a look. Looks pretty normal. So there it is in my home directory. No FTP client, using normal commands. But how far can I push it? Here I go ahead and I run head on ftp.debian.org/debian/readme. And it looks pretty authentic. So unless I went ahead and faked this entire session, we now have a translator in action. I finally used the -G flag to set trans to shut the FTP-FS translator down. G means go away. And we do an ls, take a look, normal file, remove the node, and all done. So let's talk about security. I've shown user power, all the new neat things you can do. What about security? Well, the Unix model is quite weak. Take a look at BugTrack, and we find lots of buffer overflows, SUID exploits everywhere. And my favorite, this is my new favorite buffer overflow, is the WFTPD buffer overflow. My goal is to port WFTPD to Hurd, and all these buffer overflows will be completely immune. And I think it'll be great, because there's going to be all these new buffer overflows that are going to come out, and everyone is going to be attacking WFTPD on Linux systems and on BSD systems and on Solaris systems, but they won't be able to do it on the Hurd, because although they'll break in, it's not going to work, because they'll have no access. And this is what I'm going to show you in a minute using an FTPD client. It's beautiful. I love it. You can see I'm all excited. So, where do these exploits come from? Daemons must run as root to access certain resources. Okay? When we start up, we need to go ahead and open a port. For instance, FTPD has to open port 21. And ports below port 1024 are reserved to the super user. So that's one reason. But the second reason, or another reason, is that processes cannot raise their permission in the system. There's only one thing that we can do. We can lower our access in the system. When we start up, we have a certain user ID, and we have an effective user ID, etc. But in reality, all we can do is lower our permission. Once we're already up and running, that's it. And whose fault is this? Why can't we raise our permission in the system? It's the kernel's fault because there's no interface. So how do we change this? Well, my conclusion is that the traditional security model is too limited, and we need a new interface. But one thing that we'd like to keep in this new interface is backwards compatibility. The solution that we've employed in the Hurd is to use identity tokens. Using this method, we have complete backwards compatibility. And it's much, much, much more flexible, because an identity token is not an inherent part of a process. You see, again, we've gone ahead and taken something that was considered a whole, and we've smashed it to bits, and now we have 50 million pieces all over the place, and magically they all work. So it's great. So user IDs and permission in the system are completely taken away from the process, and they're another entity unto themselves. So, identities. They can be obtained at any time. It's a token, something that you can hold in your hand, you can play with. It's not an attribute of me. It can be destroyed, and we can give them away to those we trust, to those we don't trust, and compromise the system security. That's good. But, Unix goes ahead and lets you shoot yourself in the foot. I mean, hell, we give you the gun. It's loaded. The Hurd implementation, what have we done? Well, in order to get this all right, we need some cooperation in the system. And we need someone to actually do the management. This is handled principally by the authentication server, also called auth. It's this server that actually creates the tokens. It acts as the trusted mediator between clients. It verifies tokens and validates them also. And the location that it listens on is /servers/auth. There's a secondary server called the password server. It's not critical, but it hands out identity tokens when a user has successfully authenticated himself. Excuse me. And it lives on /servers/password. Let's actually look at an example, see how it works. I've gone ahead, I've written up a getAuth program. Get-auth program takes two parameters. It takes a user ID, and it takes a password. The goal of this program is to connect to the password server, get a new identity token, and actually give this to our parent. Okay? So I'd call this from the shell, for instance. I'd say I want to become root. Type the root password, hit enter, and if I gave the right password, I should get the ID. It'll be in my ID set. So this is important. We're actually looking up a resource, using a resource, and then taking that resource and giving it to someone else. So 3 important concepts. And here's the entire program. Tested, debugged, works, and it's how many lines of code? About 17, 18 lines. And this is minus the 5 includes, because my screen is not big enough. Okay? First thing we do is we have to do file name lookup. Okay? And this gets us a port to the password server. If you notice, I've gone ahead and used 0 for the create flag and for the open flags. This is because we're not actually doing any type of file I/O, and we're just using a regular RPCs. So there's nothing we need to do. And the create flags are 0 because we assume that the node exists. If we go ahead and see that the password server equals mach port null, that means we failed. Either the password server is not running, we did not have permission to access it, any variety of reasons. Now we go ahead and say password check user. This is an RPC, another remote procedure call. This RPC is understood by the password server. If I were to go ahead and use this RPC on the auth server, it would write back and say, I have no clue what you're talking about. Why are you telling me this? So this is an RPC that's only understood by the password server. And of course by its clients. So if I'm a client, I need to use the appropriate protocol. In this case, the protocol involves password check user. The first argument we pass in is the password server port. Okay? Second argument, the user ID. Third argument is the password. And finally, in order to claim our resource, because the point of this RPC is to get an authentication token, we go ahead and we pass in a reference to auth. Auth is where's auth? An auth underscore T. And if successful, this will hold the authentication token when we're done. So after that, we check the error. If there's an error, we go ahead and report something and say, hey, it's wrong. Third, we use the getProc call. GetProc is just a macro to get a port to the proc server, which is one of the other core system servers. Another system server that's very important. And we use this port to go ahead and get the message port of our parent. Okay, our parent is get pp_pid. This returns the PID of our parent. And then we can use this RPC to get its message port. The message port is special in the Hurd. It is a port that all programs in the Hurd have or should have, which is to say that it's kind of important. This port is managed by libc, our C library. And it's where special Hurd things happen, or where you can add things, certain Hurd extensions. And it's used, in this case, to send a authentication token to the parent. So our parent is always listening on this, because as soon as it starts, libc starts a thread listening on this port. So as far as our parent is concerned, when we code it up, it doesn't actually need to understand any of this. This is all done in libc. We get our parent's message port. And finally, we use another RPC, which is the message add auth RPC. This RPC takes the message port, or a message port, an authentication token, sends it on that message port. Our parent, in this case, will go ahead and look at the message, see that there's a resource inside, which is an authentication token, and add it to its set of authentication tokens. So, enough mumbo jumbo. Let's look and see what happens. Do a file name lookup in the root file system. Get back password server port. Now we use the auth server. I wrote the auth server, but I'm wrong. It's the password server. We send it to this is a error right there. Auth server should be password server. So we call the password check user with the password server port. Get back an auth token if all is successful. Call our port again, the port get message port, and we finish it off. Let's see it run. The IDs command goes ahead and lists all of the current accessible IDs to us. This is a Hurd extension because in Unix, what we traditionally use is the ID command. It's limiting for us because in Unix we only have one ID. Want to maintain backwards compatibility again. And we've gone ahead and said ID. Well, we're doing IDs. Ha! Genius! We'll call it IDs. And it works, which is neat. So we have our IDs command. And I've gone ahead and highlighted in red that I'm just Neil, no one special, before I actually run anything. So I'm at my shell, and the user that I currently am is Neil, and my group is Neil. I go ahead and run and get auth. I provide 0. 0 is the super user, just like in any Unix-like system. And the password that I say is bar. Take a look. Did I get the root ID? Is it now part of me? No. Thankfully no, because I gave the wrong password. Although it would be a great exploit. And then I go ahead and try getting a different user ID. For instance, user ID 1001. And again, I provide the password bar. Take a look at my output, and here we see foo is added right here. So now I have several different user IDs, and I can switch between them just like I switch between using multiple groups. It's a pretty neat idea. And what's even neater is that we can destroy them too, which means that I can go from having all of these IDs to having absolutely no IDs, being unknown. I can still run programs that unknown users can run, but I effectively have no permission in the system. Most servers will reject access to me. They'll say, I don't know you. You have no right to be here. And will ignore any RPCs that I send them. This is absolutely incredible. And I will show you why right now. No magic. Unix daemons and the Hurd security model. FTPD. Very often exploited. It's great, isn't it? Everyone runs FTPD, and we exploit them all the time. How does it get exploited? Well, runs as root during startup. Needs to bind to port 21. Runs as root during the authentication phase because FTPD does the actual authentication. This is the problem. And then it goes ahead and it drops. I repeat that, drops privileges once the client has been successfully authenticated. Which means that FTPD, while it's talking to a client over a socket, is running as root. And only once you've given a successful login and password will it drop permission. This is Incredible. Stupid. Makes no sense. We should run with no user IDs. And when a user goes ahead and gives us a correct password and username, we raise the permission. This only seems logical, but we don't do it. Well, we should do it. And in the Hurd, we do it. I love it. It's poetry. So, we have Hurd. Runs with no identity. And only when the user authenticates himself do we talk to the password server and we raise our permission. I'll take questions at the end. And it raises the permission of FTPD, which means that if I go ahead and I exploit FTPD with a buffer overflow, nothing happens because I have no permission on the system. Nothing. I can't do anything. You may as well give a right username. It's just better. Whereas in the Unix model, you get more permission if you give the wrong username and you run crazy commands. Better. Yes. So, the level of access on startup, it's the same. We need root in order to bind to port 21. But in the Hurd, and unlike in Unix, we immediately drop root permission and we become no one. This means that the window of possibility to exploit FTPD is basically nil, because during that phase, FTPD is talking to no one. No one at all. We go ahead and receive clients, and we have the authentication phase. During this phase, Unix is running as root, and we're running as no one. Root, no one. Can I say it again? Root, no one. Root, no one. And then finally, we authenticate, and we become the user. So let's look at what an algorithm for running FTPD under the Hurd should look like. This is not WU-FTPD. Not yet. We make a socket. We listen on the socket. And we immediately drop all of our permission. Unknown in the system. Basically, all we can do is run. Finally, we go ahead and we listen. We're listening. We're no one. I'm no one. No one. And a user comes in. So we go ahead and we fork off a child. And the child goes ahead, does an accept. It runs some code to get a username and password. And finally, we call password check user. Successful, we start an FTP session. If we fail, we close and we say, hey, you're trying to exploit me? But it's a big joke because it doesn't work. So here I am. Speed. All these beautiful extensions. But do we have speed? No. None. Who cares about speed? No. Really. If it's not secure, no matter how fast you go, it doesn't matter. I don't want to get in a jet plane and know that I get to Boston in 15 minutes, but I have a 2% of getting there alive. That makes no sense. I'll take my time. Thank you. 8 hours. I can deal. 15 minutes, 2% chance of living. There's no way. That's like what you're doing when you're running WFTPD. Eh? Are there any WFTPD hackers here? Because you must hate me. But do other people care about speed? Well, who are the important people in the world? Ritchie and Thompson, my heroes. Yay! Well, they said in 1974, in the Unix time-sharing system, which was the paper they wrote, early versions of the operating system were written in assembly language. But during the summer of 1973, it was rewritten in C. The size of the new system is about 1/3 greater than the old. Since the new system is not only easier to understand and to modify, but also includes many functional improvements, we consider this increase in size quite acceptable. So we're talking major improvements when Unix went from assembly to C. And we think that we have equivalent steps in the Hurd. We've gone ahead, we've ripped the kernel apart, we've really embraced the original Unix philosophy, and we rock. Woo. No, we're not yet optimized, we're not even profiled. I think that, in fact, we can be faster than monolithic kernels. If you look at, for instance, Linux or any of the other big kernels today, there is a lot of code there. A lot. We're talking millions of lines of code, practically. Or it seems like it. It takes a while to read through. And you just cannot understand all of this. I can, at least. And I don't think that any of the developers understand every single interface and every single side effect. In the Hurd, we go ahead and really create the boundaries. And if you violate certain protocols, it's just unacceptable. I think in the future, this will really pay off. Because understanding one piece of the system is all you need to code for that piece. You do not have to worry about side effects for other pieces of the system. So while everyone is trying to debug their code, I'll be writing code. State of affairs. I was originally going to call this State of the Union, which is a big joke. Because the State of the Union address in the United States is the speech that the president gives every year. And he says all the great things he's going to do and all the wonderful things he did last year. So here's all the great things that we haven't done and all the great things we're hoping to do. For instance, we haven't released since 1997. Haven't. I mean, go ahead and count that. That's 1, 2, 3, 4. Almost 5 years. Woo! Long time. Long time. But we are far from dead. Far. We're actively developing. We're finishing the feature set. And we're stabilizing. Why don't we release? Good question. That's going to be the first question. But now it won't be. Because users, although I love all of my users, I think it's great when you have people using your code. It's just like, ooh, warm, fuzzy feeling inside. But users are annoying. They ask stupid questions. They waste my time. No, honestly, users are nice. Once you have all the nice documentation, you have nice installation methods, things we don't have. You think OpenBSD is hard to install? We bring it to new levels. New levels! I swear. It's great. We're based on Debian. Approximately 50% of the programs are compiled for the Hurd. I think this is a pretty good feat. We have GCC, LaTeX, X386. All of these basically work. It's not difficult to port a package. However, there are over 5,000 packages in Debian. So our really big problem of why we only have 50% of the archive compiled is lack of manpower. But this only 50% is huge. 2,500 packages. It's not bad. So once we go ahead and really implement some of the missing features and get more people, more developers, not users, developers, interested in the Hurd, we'll really take off. Drivers. Our current drivers are ripped quite violently, I might add, from the Linux 2.0.38 base. Old stuff. Ancient. I look at this stuff and I cringe. It's nasty. One day we'll use OSKit. This is a package developed by the University of Utah. And it's cool because we don't maintain it. Good stuff. One thing I love is delegation of authority. Give me authority and I will happily delegate it to everyone. Because afterwards everyone looks at you and goes, ooh, that's cool. You did a good job and I didn't do anything. It's great. But we are not slow. Yes, the Hurd is slow, but we are not slow. The Hurd is a redesign and an implementation. Compared to Linux, Linux is only a re-implementation. This is going back to one of the initial points I made. Linux has succeeded Because the interface did not change. We think interfaces are hard to write. But we've spent lots of time on it. Over 11 years writing these interfaces. Not me personally, but other people, and me recently, have written these interfaces, and we've tested them. We've thrown interfaces away because they stink. We've written lots of code, and then we've deleted it. There's nothing worse than that. It's just an awful feeling. You spend 3 weeks working on this cool code, and then you send it in, and the developers say, wait a second, that sucks. What were you thinking when you wrote that? You want to kill them. But in the end, you realize, oh wait, they were right. And you rewrite your code 15 times. And 3 months later, it's accepted. And you're like, oh yeah. But that takes a while. So we have tested a lot of new, unproved concepts. We're proving them, hopefully. And not a lot of people. We have 5 to 10 major people, or people actually hacking on the Hurd, which is not a lot compared to some other projects. So things take time. Conclusion. The Hurd's cool. Wait. I'm not done. That was just my conclusion. Seriously. A lot of new ideas. Give power to the user. We're secure. And we really work. It really works because it works today. And the example that I showed you, all the examples that I showed you work. This isn't theoretical. We have a proof of concept. And it's not bad. Pretty stable. And we like it. So, mostly works. The end. Hurd resources, other things. Thanks for coming. Now you can clap. Thank you. And now I'll field questions. No questions? Okay, one. Yes?
How does it work to assign rights to port numbers? If anybody can write a TCP daemon, can anybody bind to port 80 and accept TCP connections? Or how do you handle that?
So the question is, if I understood it, you write a TCPD daemon, and you want to prevent people from writing to it, right?
So basically, in a Unix system, if you have a standard Unix system, the kernel says that that only root can assign to certain port numbers.
Right.
And the way I understood it, basically anybody could write a TCP/IP subsystem. But how do you assign the rights? Who controls? Who's allowed to bind to the network card and accept TCP connections?
Well, the network card is basically owned by root because it's hardware. So in the ideal world, ETH0 would be a node on /dev. So /dev ETH0 would be a bridge to the Ethernet 0 device. This has standard Unix permission. By default, it would probably be something along the lines of 700 or 600. And so if root wants to delegate ETH0 to someone else, that's fine.
So it would be possible to do things like giving one IP address give one IP address to the HTTP server. Say the HTTP server can do whatever it likes with this IP address and not interfere with any other things on the server. Would that be possible?
I think that would be possible. I haven't seen an implementation yet, but I can say that it is definitely possibly possible.
Okay, thanks.
I assert that. Yes.
Is there still a 1 gigabyte limit for the X2 file system?
Yes. And I'll explain that if you want. We go ahead and actually memory map in the entire disk image or the file system image, which, given the Intel architecture, is only 4 gigabyte virtual address space. Certain limitation there. You need to reserve some of that for libraries and stack and things like that. So obviously a 1 gigabyte limitation in a world where my brother has a 60 gigabyte hard drive is not going to do very well. But again, this really comes down to manpower. It's completely... Oh, I spelled Europe wrong. Yeah, God. Yeah, in a world where 60 gigabyte is pretty normal, we need to do something about this. But this comes down to manpower. 5 to 10 developers, lots of different things on our plates. So we have different ideas on how to implement this or how to re-implement ext2. And we're hoping to do that this year. Let me readjust that. I am hoping to do that in 2002. But hey, who knows? Right there.
What about collaboration between Linux and the Hurd developers? For example, for sharing drivers also.
Well, the Linux people think we're on drugs. Honestly. They wrote this. They think we're on drugs. I don't know what to say. I mean, they think we're on drugs. Not right now. No. Does that answer your question? Not really? Well, Linus said it. Does that add any authority in your mind? Linus thinks we're on drugs. No. The Linux people really like speed, and they're not really concerned with some of these issues. For instance, one of the major issues that was recently brought up is the mmap issue using the user copy flag. And that's why Linus thinks we're on drugs. And this actually has some serious security implications under Linux. The lack of it. And I think it's missing in other systems too. The map copy flag goes ahead and allows a program to memory map in a file. And then if that file is ever changed, it goes ahead and has a copy of it made. Well, who really cares about this feature? Well, this is actually a very important feature when it comes to shared libraries. You have, for instance, the C library, and it's mapped by every single program in the system. Let's say I want to go ahead and upgrade the C library. Well, if I go ahead and just memory map in the C library as normal, which is what normally happens, and then we go ahead and actually change the file in the middle. Okay, so we're in the middle of an upgrade. We've changed part of the C library. And then another program, because we're on a multi-sharing time, that system where multiple users are logged in at the same time. And goes ahead and tries to access the shared library because he's called a new routine. He's faulted in another page, but we're in the middle of updating that page. He segmentation faults. 15 other programs segmentation fault. The compiler segmentation faults while it's installing the library, and your system goes, ah! I mean, that sounds bad. And it is. This is bad stuff. What we need is user copy. This goes ahead, and while it's changing, we have a second copy, and all users of libc will use that. So I invite everyone to go home tonight to go ahead and get a second copy of libc. Okay? Now you go ahead and you change the code so that instead of using symlinks, it uses hard links. And well, you don't even need to do that. You can just go ahead and copy. Yeah, that's good. Here, I'll show you right now. All right. What we need to do is we just copy. Oh yeah, that's right. How do I do that? Control and right mouse click. That doesn't do it for me. An Xterm? Jeez, guys. Xterm, control and right mouse click. That doesn't work either. Oh. Minus FN 8X20. Okay. That didn't do it at all. Okay, 10x20. Oh yeah, that's huge. There we go. All right. So we go ahead. We do copy /lib ld. No, not ld. Lib c dot so. Okay, we copy this to /temp /foo. Okay, and now we go ahead. We do copy /temp /foo. Right on top of lib c. Okay, so this is a regular copy. Okay, and now normally I would go ahead and hit enter, and I will. Oh, but permission denied. I'm not going to crash my system. Are you guys nuts? So, normally you go ahead and try this, and I invite all of you to try this tonight on your personal favorite operating system. And a program will go ahead and try to fault in a page in a part that has not yet been written, okay, because we've gone ahead and truncated the file, and now we have no libc. So, a fault, segmentation fault, system goes down, great panic. It's beautiful stuff, huh? Ah, awesome. That's all you need to do to crash your Linux system.
If you're root, you can break your system anyway.
Oh, sure.
And if you do it properly as root, you don't write over the currently existing libc. You rename the new version on top of the old one, which is atomic and doesn't break anything.
Well, that's atomic, but that's not cool. That's a hack. That's a huge hack.
Right.
And
I don't really see how this is an issue.
This is an issue in my mind, which is probably why you're not on the Hurd development team, because you don't see this as an issue. For instance, Microsoft doesn't even know we exist, but they seem to hate Linux. I don't know why. They hate open source. Microsoft hates open source. I don't know. I think it's pretty cool stuff. Free software. It rocks. But Microsoft says, no, don't use them. It's security issues, all of those things. And you say this is not important. It's just a little security issue, and, well, you know, no one uses shared libraries anyways. Or if they do, they upgrade them correctly, follow the prescribed manner, 3 doses per day.
I'm not saying it's not a security. It's not a security issue because you have to be root to break the system. And if you're root anyway, there are lots of other ways to break the system. I'd only call it a security issue if you can use it to raise privileges or do something you're not normally allowed to do.
Mm-hmm. Well, shared libraries do not have to be installed as root. I can install shared libraries and you can use them.
Then that's a security issue because I'm running code that you've written.
Oh,
and
yeah,
if
true.
I do that as root, then I've got other
Don't
security
use the
problems.
Hurd, trust me. I put lots of backdoors in Hurd. Lots. Whole bunch. Yeah. Shh. Don't tell anyone. More questions? Right there. Oh, wait, right here. And then back there.
What does OSKit do?
OSKit is a collection of standard operating system-like components. For instance, it has the drivers are wrapped in glue code from Linux, from FreeBSD, from NetBSD. And this glue code allows us to call these drivers in a clean fashion. And it provides all the dependencies and everything like that. It also provides a basic memory management kit and a variety of other components which are central to an operating system. This allows people that are developing experimental operating systems to go ahead and not have to worry about all the details. They can focus on the idea that they're interested in, really go ahead and implement it, and then as they see fit, they replace different parts of the OS kit. For instance, the memory management is something that's kind of interesting depending on your operating system. So we want to go ahead and replace that in OSKit with our own, because ours is going to be better. It knows more about our system. But when we're starting off, it's nice to go ahead and write 15 lines of code and be in protected mode and have support for SCSI. That's pretty neat. So going ahead and using OSKit, integrating all of the central Mach components, allows us to go ahead and skip a lot of things that we're not interested in and to focus on writing the different servers and translators. Does that answer your question? Yeah? There was one back here? No. Did you want?
If you're talking about porting packages for Debian, about how much do you need to change them? So let's say if a new version comes out, do you have to go all over it again? About how many lines do you need to change to get it running?
These are generally assumptions that programmers have made that are wrong. Mm-hmm. The GNU Hurd strives to be a POSIX-like operating system. POSIX is a standard, and there are a variety of different ways to interpret the standard. And application writers need to go ahead and acknowledge all the different ways that, or all of the primary ways that a standard can be interpreted. A lot of programmers will actually go ahead and program for one operating system. They'll program for Linux. And they'll introduce these little Linux-isms that are just a pain in the butt when they could do it right by adding one line of code.
So basically, you're fixing the programs, and after your changes, they would still work on Linux. So you don't put in anything that only works on Hurd, but you take out things that just only work on Linux.
We never do that, no. If anything, we might supplement it by adding new code to take advantage of Hurd features, but generally that's not necessary because the Hurd is mostly transparent.
So theoretically, it wouldn't be a problem if the upstream maintainers put in your changes, they don't hurt anyone else, and it would work automatically on the Hurd.
Yeah, that's what our goal is, to get these changes integrated upstream. And I'd say on average, given a program to compile it on the Hurd, it usually takes about a 10-line diff to get it to work on the Hurd. 10 lines, that's all it really takes. A few compiler errors, change a couple things, and you're off.
So you don't put in any of these message passing features or anything like that just to port a program? That's just...
No, that's part of libc.
Okay.
That's all part of libc and was to illustrate how the Hurd works. But again, libc handles all of these interactions. Right there.
So most of the improvements you make will increase the chance that the programs work on other Unix-like platforms because they make the programs better conform to the POSIX standard.
Exactly. We think we're good coders, and we fix things, we think. And we usually do a good job. Right over here.
The programs that are ported to Hurd conform the POSIX standard, but they don't use at that point of time the special extended features of Hurd, and so they don't use the benefits of Hurd.
No.
So it would just be another Unix, and if I write a program using all the good stuff of Hurd, it won't be able to run anywhere else.
No, I disagree there because I would say 90% of the benefits of Hurd are transparent. There are multiple identities which are used completely transparently. The program doesn't really know that it has multiple IDs if it's just using POSIX calls. So from the command line, for instance, I start an Emacs session editing one of the system files, and it's just running as a normal user. I'm about to save it, and I realize that I was a normal user, don't have permission. So from the command line, I go ahead and I say add auth, I say the PID of Emacs, and I say add the root ID to Emacs. Bam. Magically it happens, Emacs has the root ID. I go ahead and I run save file again, and it saves where 5 minutes ago I didn't have permission. Just magic. Using translators is something else. Completely transparent. You don't have to add anything to your programs to take advantage of translators. For instance, I showed you the FTPFS translator earlier. I used ls. ls was not modified to handle that behavior, nor was head. These are completely transparent features.
But the sample FTP daemon you showed, that was special systems, special code written for Hurd.
Absolutely.
You could do that as a wrapper around the existing FTP daemon as well. Say it, you have root privilege now. Now you seem to have created a socket. Now drop all user IDs, become nobody.
Yep.
The user has logged on. But how could you intercept these system calls? Now you have created a socket. Now I tell you, drop your privileges.
Well, just write a few changes in your program.
Yes, but these changes have to be done in the FTP daemon.
Yes, of course.
Okay.
Because these are extensions. These are extensions to the API. So if you want to use these extensions, you have to actually code them in. But we feel that we've made them relatively easy to use, that it's no different than using an extension on any other system. For instance, portability between BSD and a Linux-like system, you have certain configure checks or if-defs that you just need to make. So adding another one for the Hurd is not a big deal. It's an extension. If it's not available, we don't use it. Over here.
Looking at the example of the FTP daemon, I imagine that it is just a small part to change compared to the whole FTP daemon.
Yeah.
That these are just a few lines, and so most of the software and the complicated handling of the FTP protocol and so on would be the same on all platforms.
Absolutely.
And so I think these changes are easy to manage, and they are relatively easy to manage when not accepted by upstream, because those are a few small changes, and so I think it's not such a big problem.
Yes, I think taking advantage of Hurd special features is relatively non-invasive. So it should be embraced by everyone. Yes, Hurd. Got your cheerleaders? Da, da, da. More questions?
What prevented you from running your laptop with Hurd?
We don't have support for the i810 AGP adapter. So I have Hurd running on here, but I can only use it under the console. So it's a pain in the butt. And you can't use MGP on the console. So that's my problem. But normally I run Hurd on a day-to-day basis, and that's my primary development system.
One thing that worries me slightly. One thing that worries me a bit about the process of gaining privileges in the Unix model, you know that if a process drops privileges, it won't be able to get them back. But in the Hurd, theoretically, any process which runs as anybody could get basically root rights, which would make, I'm not saying this is less secure, but it's different, which would make it more which would require different analysis to find out if a system is secure.
Sure.
Has anybody done research in that direction? Or are there any ways to say, I don't ever want to get any extra privileges, I refuse to get them if somebody wants to give them to me?
That's an interesting idea, and I don't know if that's interested, but
because it would be one potential exploit. You have gain privileges somewhere and say, okay, let's give root rights to the FTP server, even though it doesn't want it.
Yeah, I think that's a great idea, and maybe I will consider adding that or proposing it. If you have other good ideas, we have a mailing list, and you can send them, because you sound like a developer type guy. See, don't want users, want developers, and you sound cool. So, just go ahead to hurd.gnu.org. There's all the mailing lists there. There's 4 of them, and subscribe. Send me these great ideas. Other developers here too, join us. Users, use something else for a few years, come back later.
What about running Hurd in VMware?
VMware is non-free software. What about it?
Or Plex 86? Plex 86?
Plex 86. I don't know about Plex 86, but what is it? Is it Box? It doesn't work.
It's free software.
Oh, yeah, yes, I know it's free software, and we do have people that are helping the Plex 86 people getting it to work. Or Box. I think that's another option. Yeah, Box works. BOCHS, is that?
Box is integrated to Plex 86 in some parts.
I'm sorry?
It's integrated in some ways.
Okay. Well, apparently Box works,
developer
but
is the same.
Yeah.
It was just fired.
No, so we need help with Plex 86, but Box looks good. There we go. But it's slow from what I hear. Oh, slow. But who cares about speed, right? Other questions? Okay, well, I'll be here. I'm leaving in 2 days. So come and harass me. Developers, not users. Developers, come harass me. Okay? Thank you for coming. Have a great rest of stay at CCC. And ciao. I forgot something. Developers stay, users leave. Okay. Developers, people who like Hurd, we're having a little workshop tonight with us and some L4 people. L4 is another microkernel that is being developed in Germany by Karlsruhe, University of Karlsruhe, and some others. What?